Good morning, everybody. Can you hear me okay? Yeah, sounds good. Okay, I'm curious. I want to start by seeing a show of hands of anyone who's heard of the model evaluation tool software before. Okay. I guess keep your hands raised if you've actually used it before. All right, sounds good. So Model Evaluation Tools is a software package that's been developed and supported by the Developmental Testbed Center for the last 10 years or so. And there's a large group of people that work on it. Myself, I'm the lead engineer on the MET package. Tressa Fowler, who's sitting in the back here, she is a statistician on the MET team who basically tells us what to do correctly. And then there's a large group listed here. We have a good mix of software engineers, atmospheric scientists, and statisticians. So in the next hour, I think I have Tress and I combined have something like 95 slides. So I'm going to move through them very quickly. We teach a 2 or 3 day tutorial on the MET software itself, where we go through each tool in a lot of detail and you run through the exercises. Obviously, there's not time to cover it in great detail here. I just hope to give you kind of a broad picture view of the types of functionality that are available in this package to hopefully spur your interest and encourage you to go seek more additional resources and learning opportunities. So I'm going to talk about the MET software, give you some information about the MET viewer database and display system, talk about what we've been working on the last couple of years with a package we call MET Plus, which is intended to automate the running of MET. Tressa is going to give us about 15 minutes of a talk about the science behind ensemble verification. I'm going to dive into some more detail about the ensemble stat tool in MET, talk to you about the enhancements in the current release of MET, which is MET 7.0, and what we're working on for the next release in MET 7.1, and then just a final slide on how you can use MET in a Docker container. So MET is a software package written primarily in C++ with some calls to some Fortran libraries. It's compiled on Linux or Mac with GNU, PGI, or Intel compilers. Freely available, open source. There's over 3,600 registered users from 133 countries. I always find it interesting that only 30% of the registered users are actually from the United States. So there's a large international use. It's used by a mixture of universities, governments, private companies, and nonprofits. We support the MET software by giving an online tutorial and also in-person tutorials each year. We usually do 1 or 2 each year. And we have a methelp@ucar.edu help desk support, email support system, and we answer about 250 or so support tickets each year, although that number seems to be increasing recently. I mentioned our first release of MET was in 2008, which means we've been doing this for about 10 years. So this is a slide from Tara Jensen, who's the project manager of the MET team, and she found this little goofy fireworks, which seems appropriate for the 4th of July anyway. So how do you get information about MET? Here I have highlighted. Is that readable? The URL for the website is dtcenter.org/met/users. And on this site, you can find links down the left side. There's, under the user support tab, you can find FAQs, the actual online tutorial, release notes listing what we've added for each release, and also information about how to contact MedHelp. Under the download tab, you can find the source code itself that you can download and compile yourself locally. We also have a list of existing builds. So I think it was about a year ago, NOAA. So we've been working closely with folks at NOAA, particularly at EMC. And NOAA has chosen to unify their verification activities on the MET software. So to make it easier for those folks working at NOAA, we have precompiled versions of MET in a variety of places, and they're listed in red here. So within NCAR on the RAL machines, you can find it in user local. Then on Cheyenne, Thea, Gaia, and Jet. And then also operationally on the WCOS machines. I always thought WCOS was one machine. In point of fact, there's actually 6 separate nodes of it. So it sounds simple, but to compile it on WCOS means compiling it at 6 separate places. Met is available as a Docker container, and the URL for the GitHub repository is listed there at the bottom. So what is Met? What are the tools? So here I have a flowchart with a bunch of colored ovals and gray boxes. Each colored oval basically is an executable in the Met package. And each of the gray boxes represents the input and output files for those tools. The tools shown in dark green are tools that do some amount of reformatting, either for gridded or point data, kind of preparing data for use in the Met software. The ones shown in light green, so I'll use the mouse here. Is that working? There we go. These ones are utilities for making some sort of plots. The ones listed in blue are kind of the workhorse. These are the tools that actually take the forecast data and compare it to gridded or point observations and compute statistics. So that's kind of where the heavy lifting is. And then the tools shown in yellow here are the mode analysis and stat analysis tools. These tools are meant to aggregate the results of the statistics tools across multiple cases. There's a whole column of, there's 3 tools on the right side here called MET-TC, which is Met Tropical Cyclone. So a few years ago, I guess several years ago now, we collaborated with the National Hurricane Center to take their verification tools and make them available publicly, and we did that through MET-TC. So we rewrote a lot of their algorithms using the library infrastructure within Met, and have supported this to the community for the last several years. So I'm not going to talk any more about MET-TC, but if you have questions for me about verifying tropical cyclone track and intensity forecasts, I'd be happy to answer them. So since we have particular emphasis on the ensemble stat tool, I want to point out that this is the one that is with the gradient here. So it's shown both on the left side as being green, on the right side as being blue. And that's because the ensemble stat tool does a little bit of reformatting and also computes some statistics as well. And after Tressa talks and I explain what the ensemble stat tool does, that'll become a lot more clear. A lot of the verification that folks do is done using the point stat tool, which is where you take a gridded NWP model output file and compare it to a set of point observations. So this is kind of a big workhorse in Met. I want to point out that the grid stat and point stat tools are intended to be run once for each forecast verification time. So if you have a forecast that was initialized today at 0Z and you produce a 12-hour forecast, then for the 12-hour forecast, you run point stat and compute the stats for that time. For the 18-hour forecast, you run it again and compute stats for that time. Each time you run it, you can verify one or more variables and levels. And I mentioned earlier that the stat analysis tool is provided to enable you to accumulate statistics across multiple cases. What are the actual statistics that point stat computes? There's methods for computing continuous statistics on the raw fields, applying one or more thresholds to compute single or multi-category counts and statistics for thresholds of interest. For example, where is it raining? So where is a precip greater than 0? That is when you apply that threshold, you transform your continuous field into a binary field of events and non-events. Point stat includes methods for assessing parametric and non-parametric counts intervals for each of the statistics. And Tressa tells us which ones to apply to which statistics in as an appropriate way as possible. We compute partial sums for the raw fields. We also are able to dump out the individual forecast obs match pair values. There's methods for verifying probabilistic forecasts. And recently we added something called HIRA. And it escapes me what HIRA actually stands for. It's essentially doing point verification, but in a neighborhood. So you allow some, you don't require your, you allow some, you look in the neighborhood around the point location for an event. Maybe it didn't occur to exactly that lat long, but it occurred nearby. The grid stat tool is very similar to the point stat tool. And if you compare the points, the bullet points here, they're almost the same. The major difference, though, is that whereas the point stat tool compares gridded forecast to point observations, the grid stat tool compares gridded forecast to gridded analyses or gridded observations. And this data must be put onto a common grid. And I have some slides showing how you can use MET to make that easy. Again, when you run grid stat, you accumulate match pairs over defined areas at a single point in time. You can verify one or more variables and levels. You run the output of grid stat through the same stat analysis tool to aggregate results across multiple cases. Same set of verification methods. What's new here, though, is that since we're comparing gridded forecasts or gridded observations, we can now apply neighborhood verification methods and compute statistics like the fraction skill score, if you've heard of that. We also recently, in working with folks at NCEP, they like looking at taking the gridded field and computing the gradient, and then computing statistics on the gradients of the field. So that was a recent addition to GridStat in collaboration with folks at NCEP. Next, I'll move on to the MODE tool. The MODE stands for the Method for Object-Based Diagnostic Evaluation. So in this image here, in the top left corner, there's a cool-looking plot that my colleague Randy Bullock made, and this represents precipitation accumulation values over the continental United States. And then the steps in doing object verification with MODE, the first step is to convolve the data. So convolution basically means smooth the data out by averaging with points in the nearby each individual grid cell. So the third step is we apply a threshold to that mask to define basically the regions of interest. And then we restore the raw data values back inside those objects and compute object-based attributes to assess how well the forecast objects compare to the observation objects. And all of these settings are controlled in a user-defined configuration file. So what does running MODE look like? So in this example on the left, I have a forecast of precipitation. On the right, I have an analysis of precipitation. This is the raw data field. So the first step would be to choose our radius and threshold of interest. So in this case, I'm choosing a radius of 5 grid cells, and I'm looking for places where the convolved values exceed 0.25 inches. And when I do that, that identifies these black regions as the objects in my field. There's logic in MODE to say if these three objects, there it is, okay. These three objects are objects defined by applying a threshold of greater than 0.25 inches. If I were to apply a threshold of greater than 0.20 inches, then they would be merged together in the same object. So in this way, we group together these objects and we merge them in the forecast field and say, well, they're close enough to be considered as a group. Then we compare the forecast objects to the observation objects using a fuzzy logic algorithm, and we say this red forecast object matches this red observation object, and they're similar enough to consider them to be matched across the forecast and observation fields. Likewise, this group of green forecast objects matches this group of green observation objects. These blue areas in the observation area are unmatched observations, so we call them misses. And we don't have any false alarms, which would be unmatched forecast objects. So I mentioned you can control, it's up to the user to decide what their region of interest is, and you do that by applying a convolution radius and threshold. In this graphic, we show the effect of applying a convolution radius of 3 grid squares, 9 grid squares, 15 grid squares, and you can see that the level of detail, the objects go from higher resolution down to more smooth objects in the bottom right. So it really is, if you're interested in looking in assessing how well your model captures large MCS systems, you might define rather smooth objects. If you're interested in individual convective cells, you might define rather detailed. You wouldn't do very much smoothing at all, maybe no smoothing at all. So it really is up to you to decide the level of detail that you're trying to assess the performance from your model. I want to say that Tara gave me hundreds and hundreds of slides from various presentations she's given. So it was pretty easy for me to just go through and pick out the cool pictures. So this is an example of that. Since we have an emphasis on ensembles today, this is an example of running MODE on an ensemble of forecasts compared to the same observation set. So in this picture, the colored areas, the red and blue colored objects, are the observation objects. This, again, is, I believe, 3-hour accumulated precipitation. And the green shaded objects are from the individual ensemble members. These ones with the black outline are the ensemble mean objects. So on the next slide, I'll mention these blue ones are the unmatched observation objects. So on the next slide, we see an animation going through, for single initialization, going through 3-hourly accumulated precipitation forecasts from 3 hours up to 24 hours. And you can see that as, using mode, you can see how the spread of the ensemble increases with lead time. It's just kind of a nice application of mode to ensembles. So I spent a little while on mode. I want to also mention the series analysis tool. So mode, just like PointStat and GridStat, you run it once per output time. The series analysis tool is instead intended to be run on typically a time series of data. So in these pictures here, I have 3-hourly forecast accumulated precip and 3-hourly analysis precip from stage 2 on the right. And what we want to do is stack these fields up through time and compute statistics at each individual grid point. So what I have here is the series analysis tool enables us to do that. And the intention here is that you're able to see how your model performance varies over the domain. So I believe I ran this using 92 output times, so a time series of length 92. This plot here doesn't look very interesting. All it is showing us is that at each of these pink grid locations, we have the full time series of data present, 92 grid point or 92 output times. And then along the boundaries, there was some missing data, and that value of 92 dropped to a lower value. It actually is really important when you run the series analysis tool to look at the count of the total count of data at each grid point to make sure you're not to make sure you're only looking at statistics where you have enough data for the results to be meaningful. So here's an example of the base rate. So you can see, and on the left, I should mention this is looking at precip greater than 0.0 inches. On the right, greater than 0.1 inches. And so that's base rate. So obviously, this is basically the frequency at which the event is occurring at each grid cell. This is Gilbert skill score, which is also equitable threat score. No, this is, I'm sorry, frequency bias. And then a variety of other statistics. The user can configure, set up the configuration file to request individual statistics be written out to the netcf output file. Here's an example of running mode across a time series of data as well. So we use series analysis to analyze a time series of grid-to-grid comparisons. This is an example of using mode, running mode separately on many output times, looking for area. This is GFS data, comparing it to its own analysis, which is not a good way of doing verification, but it makes for a nice example. So this is looking for areas of high pressure across the globe. And you can see this nice, as the forecast increases, you can see the tendency of the objects to move from the west to the east. So what are some of the things that you can look at with the output of mode? Well, if we compare, for example, this red forecast blob to this red analysis blob at a single point in time, you could say, well, these were offset by about 4.5 grid cells. You could look at their object areas and see how they differ. You could look at how many grid points they had in common. Those are the sorts of questions you can answer with using the output of mode. But this motivated the creation of the mode time domain tool. And again, this is developed by Randy Bullock, a software engineer that has done a lot of the coding for the MET software. So this is using the exact same data set, running it through the mode time domain tool, and basically, so you can see the spatial extent in the X and Y axis. The height axis is time now. So it's kind of like running mode separately for many slices of time and stacking the objects up. So now I'm going to highlight here the forecast object 4 and the analysis object 3. And I want to show you that now we can answer things like, how does the velocity of these objects compare? So is my model too slow or too fast? Now the centroid in 2 dimensions becomes a centroid in 3 dimensions, with the third dimension being time. Instead of area, we talk about volume. We can look at the maximum intensity within the object, those sorts of things. So the mode time domain tool is still relatively new. I think the first version of it came out a couple of years ago, and we're still beginning to apply it to our test and evaluation projects in the DTC. So lots of options, and those options are controlled by ASCII configuration files in MET. And here I have just a sample of a handful of config options that are available in the MET tools. Some of them are pretty mundane. For example, the model, the description, and the ob type. These are just string literals that the user specifies in the config file, and all we do is run, we write them to the output file. So if you're verifying multiple forecast models, you need to give them some name so that you can distinguish between them in the output. So that's what these tools do. The regrid section is, on the other hand, is a lot more powerful. This enables you to regrid your data on the fly. Basically, when you're doing a grid to grid comparison, put them on a common grid so that the statistics can be computed. We recently added support for censoring data. So for example, if you're dealing with precip and you have some spurious precip values that are less than 0, which isn't supposed to happen, but sometimes does because data is messy, you can apply a censor threshold and say any values that are less than 0, remap them to 0. So using the censor value, censor threshold and value basically helps you deal with messy data. And then lastly, the last thing to mention here is the user controls what fields they want to verify. And that's done in this forecast and obs dictionary is what we call it. So these things that are enclosed in curly braces we call dictionaries. And the user says, for example, here we're looking at 3-hourly precip, and we're interested in applying a categorical threshold of when that 3-hourly precip is greater than 0 or greater than 5 millimeters. So this is certainly not a comprehensive list, just to give you the look and feel of what the config files are like. I mentioned automated regridding in MET. So here on the left, we have a 1/4 degree HWRF output for a Sandy case, where we have 6 hours accumulated precip. And on the right, we have a 4-kilometer stage 4 grid to which we want to compare this forecast. So these grids are very different. How can we do the comparison? So in the regrid section, you could if you set the 2-grid option to forecast, then that will automatically regrid the observation data onto the forecast domain. And when you compute the differences, you end up with 20,000 matched pairs at a 1/4 degree resolution. Alternatively, you could set the 2-grid option to obs, and that will automatically regrid the forecast data to the observation domain. And that will give us about 700,000 matched pairs at 4-kilometer resolution. Some of you may object and say, well, you shouldn't take this low resolution grid and remap it to a high resolution domain, and I agree. So maybe instead you want to choose a middle ground, and this is an example of, instead of setting 2-grid to forecast or obs, you set it to a 3rd grid, and you remap both of those data sets to a common grid. In this example, I've used NCEP grid 130, which gives us 70,000 matched pairs at 13-kilometer resolution. And you could talk to Tressa or other statisticians about what is the most appropriate way of doing the regridding. I'm just here pointing out that these options are available in the software. Okay, how do you control what the MET tools actually do? So in the point and grid stat tools, in the configuration file, there's a section called the output flag. And you see long lists of abbreviations. And basically, each one of these abbreviations stands for a line type. So you can't control the level of detail statistic by statistic. You don't say, well, I want root mean squared error, but I don't want mean absolute error. But you control it by groups. So you say, for example, I want to do categorical verification. So I'm going to define my threshold of interest, like precip greater than 0, temperature less than 273 Kelvin, something like that. And these line types give you information about doing categorical verification. These sets of line types give you continuous statistics, like root mean squared error, partial sums, that sort of thing. This SA, L1, L2, this is for anomaly statistics, so like anomaly correlation. The ones beginning with V's give you vector wind stats. Ones beginning with the P's are for probabilistic statistics, and we'll talk more about those later today. The ones beginning with N are the neighborhood statistics. I mentioned fraction skill score. These are only available in the grid stat tool when you can do grid-to-grid comparisons. And lastly, the MPR line type stands for matched pairs, so individual forecast obs matched pairs. So you're able to configure point stat, for example, to say, if you've computed statistics over 10,000 matched pairs, you could have it write out each forecast ob matched pair value so you can dive in as deep as you want. Operationally, that isn't realistic. It's too much data. But when you're investigating a case study, maybe you do want to dump that out and look at very fine detail at your data. I mentioned line types. So here's an example of a single output line from the point stat tool. This is a 2x2 contingency table, and I've shown here the column name and the value. So you can see that there's a lot of, the first 21 header columns are common to all the output line types. And then here are the ones highlighted in blue. These are the actual data columns that are associated with the contingency table count line type, which is basically just a 2x2 table of hits, misses, false alarms, and correct negatives. So you've used MET to generate all this ASCII output statistics. And now what do you do with it? For the longest time, we weren't supporting MET Viewer to the community. We're now transitioning and beginning to support the community. Tressa actually is working on the user's guide for how to install and use MET Viewer. So what is MET Viewer? It is intended to take the ASCII output of MET and load it into a database and give you ways of interacting with that data to make plots of your statistics. So here's the MET output that we just generated, and we run it through a loader, and we load it into a MySQL database. Currently, MetViewer uses MySQL, although Tatiana Burek, the developer for MetViewer, has extracted out all the stored procedures from the database, making it easier to swap it out. So when we move to using it at EMC, they really prefer Postgres. So we may have the ability of doing Postgres. Likewise, folks over at NOAA GSD are investigating the use of Couchbase, which is you mentioned, Unidata, right? It is a NoSQL database, right? And is a lot easier to expand. So MetViewer has a web app that I'm going to show several slides on, and it queries data from the database, passes that off to R scripts, which do things like event equalization, aggregation across multiple cases, and ultimately R makes the plots that we serve up through the GUI. Alternatively, you can use the MetViewer batch engine to interact directly with the database to make plots through R. So what are the options of the GUI? Here I'm showing the URL to the public-facing instance of MetViewer here that's running here at NCAR. How would you use this GUI to make a plot? The first thing you need to do is click on the list of databases and select the database that contains the data that you want to plot. You pick from one of the existing plot templates. So, and I think I have a slide that make these a little bigger to see what they are later on. So basically you pick the plot type that you want to make. You pick the variable and statistic of interest, for example, maybe 2 meter temperature, root mean squared error, for example. You select what you want to go on the y-axis. So y-axis variable. Actually, this is basically if you're making a line plot, what defines the lines? Typically, that's different models, maybe different lead times, that sort of thing. You can pick how you want to stratify your data. So, for example, if you have output for the eastern CONUS and the western CONUS, and you only want your plot to contain data for the eastern CONUS, initialize at 0Z, applying a threshold of greater than 0, that's where you would stratify the data by defining the fixed values. You select what goes along the x-axis. So you select your independent variable. You select how you want to summarize your data. Do you want to aggregate them across all the cases, or do you want to compute a summary, like the mean value, the mean daily value? You can choose how you want to format the series on the plot, so format the lines. You can pick titles and legends, X labels, Y labels. And ultimately, once you've picked all that, you click Generate Plot. And that will generate an image here. When you have the image there, you can look at these tabs. The plot tab obviously will have the plot image. But each plot has a single XML file that defines it. So that's available on the second tab. The nice feature is if you have the XML and you save it locally to your disk, You can then go back to MetViewer and click Load Existing XML and upload the plot XML that you just made. That'll go through and repopulate all the drop-down menus. So you can basically get back to save your state. So if you make a plot you really like with MetViewer, save the image, also save the XML so that you can get back to where you were. So here's an example of, yeah, the plot showing up. So what are the available plot templates? There's series plot, which is basically lines in a plot, box plots, bar plots, receiver operating characteristic plot, reliability, ensemble spread scale. You can read the rest. I'll highlight the last one. Contour plots is a new version, or is a new plot type in the current release, I think version 2.5 of MetViewer. Okay, a lot of the test and evaluation we do with the Developmental Test Bed Center is to say, is Model A any better than Model B? And we use MetViewer heavily in answering that question. And what we do is we say, we pick our, in this image here, there's a red line, a blue line, and then a green line. The green line is a pairwise difference of the statistics that go into the red and green lines, or the red and blue lines. And what we're doing is putting confidence intervals on the pairwise different statistic, pairwise different line, and checking to see if their confidence intervals do or do not include 0. So here's a blow up of that image, and basically at the 0 hour, 42 hour, 72 and 78 hour lead time, the confidence intervals on the pairwise difference line do not include 0, meaning that the difference is statistically significant at whatever the confidence level value we had defined was. I think our default is typically 95% confidence. Another nice feature of MetViewer is that the history of recent plots that were made on the system is available through this little icon here in the top left corner. You click on that, you see the list of recent plots. You click on here, you see the image. Click on here, you see the XML. So you can easily say, so you click on the XML, you can say load it to the page, and that'll automatically upload all the drop-down boxes with the options that correspond to that plot. You can save off the image, save off the XML by just clicking this little download button in the top right corner. So that's basically what the GUI looks like. In the interest of time, I'm going to skip forward, other than to say that you can also plot mode object attribute counts and attributes with MetViewer. And we've also added, I think in this last release, the ability to plot mode time domain attributes as well. The MetViewer, okay, so lots of options for configuring Met, lots of plot types to make, maybe too many. So how do you summarize it all? At NOAA, they've been using something called a scorecard, which is where you take Model A and Model B, and you say, when you look at all these variables and levels and over these multiple regions and all these lead times, how frequently is one model statistically better than another model? So in MetViewer, we added support for generating scorecards. You can pick the statistics that you want to include in your scorecard. You can specify the variables. So the first one here is anomaly correlation height. You can specify the levels. So there's multiple pressure levels listed here. You pick the regions. So for example, here we have North America's Northern Hemisphere, Southern Hemisphere, and the tropics. You specify the temporal aggregation, so day 1, day 3, that sort of thing. And then you can pick what actually shows up in each cell. So do you want a symbol showing that, I think the green upward pointing arrows mean that Model A is better. The red downward pointing arrows mean Model B is better, that sort of thing. And you can either have symbols to identify which one's better, or you can actually list the p-value, which quantifies how significant that difference is. And this is only not available through the GUI, only available through MetViewer. Or through the batch engine. Okay, I'm going to breeze through Met Plus here. So Met Plus is our attempt over the last couple of years to wrap Met and automate it using Python wrappers. So the goal here is to take a use case for doing verification and collapse it down into a single configuration file for Met Plus that will enable, basically, it will define a path through the tools available in the Met software. And so all of the tools shown here in yellow are currently included by at least one of the existing use cases in Met Plus. Here's the URL for the GitHub repo where Met Plus lives. I think it says private here, but I'm pretty sure it's publicly available. And when you look here at the repository, you'll notice a directory structure that may look a little bit odd. The parm directory is where the control file and config files live. USH is where the Python scripts live. If anyone's worked on WCOS for EMC, this directory structure will look familiar to you. This was basically the directory structure required for running operationally on WCOS, so that's what we adopted. So what does wrap by Python mean? This is an example of a parameter file for Met Plus, for our feature relative use case, where we work with folks from the Stony Brook University to identify features of interest and basically extract tiles of forecast and analysis data centered on the feature of interest, and then stack them up through time and use the series analysis tool. So here we are listing the statistics for which we want to run series analysis. We are listing the variables that we want to analyze, and we're listing some time information. So then, so Met Plus basically, with this control information, goes through and runs PCB combine if necessary. It runs, it does this tiling of the data, runs series analysis, produces some output graphics. So currently, okay, I'll also mention that the Met configuration files support the use of environment variables. So in this example here, we see that the description of the data is $name, $level. So what Met Plus is doing is essentially is just setting the right environment variables, calling the tools, the Met tools, after setting those environment variables to instruct Met what to do. So here, just pointing out that these Python wrappers build the commands to call the Met tools, and typically the input of one call is, or the output of one call is the input to the next call, and so on. We've adopted some good coding standards here, incorporating both coding standards from NCEP and also following the WCOS implementation guidelines, following PEP 8 code style, and using Doxygen and Python doc strings for documentation. Since we're working with folks from NCEP, we're leveraging functionality from the prod util package, which is the Python package that they use for, that was developed as part of HWRF. Currently, we are running Met Plus just on the command line, basically, but we know that we need to be able to call it from Rakoto Workflow, which is a workflow management system, or EC Flow. Rakoto Workflow Management System is used primarily in research, and EC Flow is, I believe, currently being used at EMC for operational runs. This may shock you. Met Plus is built on Python 2.7. Why in the world would we do that? Operationally at NCEP, they will not allow us to use 3. So we are pushing back as hard as we can. Here's some more links to where you can get the Met Plus beta release, and then you can see the, if you are interested in collaborating with us, then you can send an email to myself or the other people listed at the on the last slide. Okay, directory structure. This was imposed basically by running on WCOS operationally. Here's 3 use cases that are well documented or well tested. Track and intensity, so basically doing tropical cyclone verification. This feature relative use case I've already discussed, and the QPF use case of using GridStat to verify precip forecast. So I think our goal is to build up kind of a warehouse of use cases, maybe 20, 30, 40, so that users in the community can say, well, I want to do verification. I don't know where to get started. Let me go see what already exists, take an existing one, and modify it for my needs. So that's the motivation. So I'm going to pass it off to Tressa now, who's going to talk to us more about ensemble verification.
Hi, everybody. I'm Tressa Fowler. I'm a statistician in the DTC, so I'm here to sort of just introduce a few of the types of statistics and metrics that are available in the MET package. Ensemble verification, obviously different than traditional deterministic forecast verification. So the goals of ensemble forecasting are different, and then the math is different. So there's a whole different set of statistics, a whole separate tool that you can use if you're doing ensemble verification. And I'll just talk about probably a handful of these, quick introduction to them, and then at the end I'll have a handful of references just for you guys to take home with you if you really are doing ensemble verification. So before you do any verification of any type, but particularly ensemble, you have to ask yourself a few questions to make sure you're headed in the right direction for your verification exercise. How did you get your ensemble? This does matter. Do you have a distinct member group of ensembles where, say you just collect a whole bunch of different models together and use that as the ensemble? Sometimes that's an ensemble of opportunity or something it is called. Are you doing multiple physics where you want to evaluate them separately and see how they behave over time and differently than each other? If you're doing a stochastic ensemble, your members might be different from each other, but from one time to the next, there's not really a relationship. So ensemble member number 1 in a stochastic ensemble is not related to itself through time. They're all just random. So you want to make sure in your evaluation you don't pretend that it should be related to itself over time or that it's distinct. In that case, all ensemble members at all times are basically equal. Then, of course, in any verification evaluation, you have to consider how is your forecast going to be used. If you're just going to use the ensemble mean, that turns into a deterministic forecast, and you go back to your traditional verification methods, and I actually won't talk about that today. There's not that much time. Are you going to use your ensemble to create a probability, either via a relative frequency or some type of ensemble post-processing? Evaluating probability forecasts is mathematically different than deterministic forecasts, and so I'll actually spend the first several slides talking about probability methods. Or do you want to use the full distribution of your ensemble? That's a little harder to do. The math on that's also different, but we have a few statistics in MET that will help you do that. I see that done a bit less often, but I think sometimes that can be the most valuable way to use your ensemble. So, as I mentioned, are you going to look at individual members, or maybe the ensemble mean, a probability forecast, or the full distribution? We're not going to talk about the individual members today. So for probability forecasts, I just am going to give a quick overview of 4 different types of statistics you can do for that. The Breyer score, which probably some of you have heard of, is really just a mean squared error in probability space. A couple of diagrams, reliability and receiver operating characteristic, I'll show you. And then economic cost loss, which we've recently implemented in MET. And then I'll talk about 4 statistics for using the full distribution of your forecasts, and those we see used somewhat less, but with the options in MET, it makes it a little easier for you to use your forecast this way and to see how valuable they might be. So probabilistic forecasts are a little different. We like to think of, they forecast the temperature today to be 100 degrees, and they may be off by a couple of degrees. It's pretty easy to tell whether that's good or bad. But if I were to toss a coin and ask you to call heads or tails, it doesn't actually matter what you say. You may be right, you may be wrong. The quality of that forecast that you've made, what will come up, is none. What really is valuable is knowing if I were to do it 100 times, predicting that it would be about half all of the time. That's where the value comes in. So in a probability forecast, there is really no value except over a large group of cases, and it's hard to say if something is right or wrong. And that's true of most statistics anyway. But you can't even judge the quality of a single probability forecast. If I were to say 20% chance of probability of precip today, and it rains, is that good or bad? Well, we want it to rain some of the time. Maybe this is the 1 case out of 5 where it should. So you really do need a large set of cases. And of course, when the event is rare, you need even more, and it becomes more difficult. And that's true of any probability forecast, whether it's created from an ensemble or not. Probability forecasts have 3 qualities that make them good. One is reliability, which is really it's bias, but it's a conditional bias in each probability category. So you'd like for your probabilities to be about right. If I was flipping a coin, we'd like to see 50% on the heads or tails, but if we were to forecast 40%, that's kind of an unreliable forecast. It's biased. Resolution is important, and we have a little graphic here which shows, just for a specific set of data, we'd like to see when an event happens and doesn't happen, that our forecasting system has a different forecast for that. So we'd like to see division in our distribution of forecasts based on whether our event occurred or not. And then sharpness is another good quality. So sharpness is specificity in your forecast. So if you're real general and you have a big range of anything that could happen, that's not as useful to your user as if you can really hone in on maybe plus or minus 2 degrees instead of plus or minus 10. So that's what sharpness is. It's often hard to kind of get at all of that, but a nice statistic that at least gets at some of those qualities is the Breyer score. The Breyer score is very friendly. It is the mean squared error, really, but in probability space. So it's something you're used to, that everybody understands. It penalizes large errors a little more than smaller ones because it's a squared statistic. It has a nice decomposition. So you do some algebra and you break it down into these components. So these things add up to the Breyer score: a measure of reliability, a measure of resolution, and then here, uncertainty, which this is just a function of the observation. So it's not uncertainty like you might think about it, or like John might talk about in observational uncertainty from instruments. So you can look at the components of the Breyer score, the reliability and resolution, and get at 2 of the qualities of your forecast that you might want to know. This is an attributes or reliability diagram, which you can use MET to produce the information for and MET Viewer to produce the plot. It shows the conditional bias in a probability forecast. So along the bottom here, we have your forecast probability. So let's say, for example, 50% forecast probability, and then we go up here and we say, well, when we forecast a 50% probability of some event, maybe precipitation, how often did we observe that? We would really like for that to be also about half the cases. So when we took those observations, let's see, I lost my mouse, there it is. Did we see about half here? And if we did, then that point will fall along the 1-to-1 line. So here we have an example of a forecast with very good reliability. Almost all of these points fall along the right proportion. When we forecast 20%, we observed pretty close to 20%. The little numbers here are the percent of your cases that falls into each of these bins, and that can be important because it is often the case, particularly when you have rare events, that up here for these high probabilities, you won't have very many forecasts. And so then your diagram might look real bad up here. Sometimes there's big zigzags or something funky. That's not a problem with your forecast, it's a lack of cases. So you might wanna just change maybe you don't even have a group of 70% probability for a rare event because you're rarely gonna forecast that. So this is a nice way to look at your data, and MET can help you produce these. Discrimination is a type of plot. You need a specific type of data here where you have an event and a non-event, and then you just look at the entire distribution, say, of your ensemble to see how separated are the two distributions based on what you observed. This is not so good here. Over here, it's much better. So if you had rain and no rain, you might like to see your distribution of precip amounts be different. And of course, the sharper your forecast is, that's better. But with ensemble forecasting, you want to make sure you get plenty of spread, so there's balancing those needs. A sharp forecast is good, but spread in your ensemble is important also. And then this is just a slide about sharpness. Sharpness is a function only of your forecast, and so you can get at this by just looking at the distribution of your forecast values. But of course, sharpness is only good if you've already got accuracy. If you have a very sharp forecast that's very wrong, you probably need to change your forecasting system. The receiver operating characteristic, or ROC, is a type of graphic that allows you to look at a range, say, of probability thresholds without regards to calibration. So if you have 2 models you're comparing and one is biased, let's say it over-forecasts the probability of precipitation, for example, it's going to be tough to set a 50% threshold and compare that with the different one because they're really getting at different things because of the bias. So with the receiver operating characteristic, you plot the probability of detection and the 1 minus the false alarm rate, which is the success rate, for all possible thresholds, all the way from 0 up to 1. And so that takes the calibration issue out. So you judge calibration from your reliability diagram. And then you look here at skill. Perfect skill's up here in the top left corner. The no skill line is the one-to-one line. You can measure this sometimes by using the area under the curve. So use the trapezoid method to estimate the area, and a larger area is a better statistic. So this can be a nice way to compare two probabilistic forecasting systems without regards to their calibration. And this is available, the plots are produced in MET, and the area under the curve, or the plot points are produced in MET, and the area under the curve statistic. And then the MET viewer software will produce the plot for you, or it's very easy to produce yourself in R. If you have an economic value associated with your forecast, say a cost to loss ratio, which we can sort of define very simply in a 2x2 contingency table here. Does our event happen or not? And did we take action to protect against some loss, or did we not take an action? If you take an action, there's some cost associated with that. If you do nothing and you have an event, then you probably will suffer some loss. And I don't know whether that's purchasing insurance or turning on heaters or whatever it is. You might have a cost-loss ratio. And with a probabilistic forecasting system, here's an example of a cost-loss value plot. And again, the statistics here are produced in MET, and the plot can be produced in MET Viewer. I have here 4 different models, so just some different diagrams to look at. Your cost to loss ratio, so this is just the ratio of how much it costs to protect versus what you could lose, varies along here, and then the value of your forecasting system. And it's pretty typical for you to have a value, peaking somewhere low in the cost to loss ratio, so you can compare forecasting systems this way by seeing what is your cost-loss ratio, and then which one, at what point is it maximized, and which forecast might be better. So in this case, like the black and the red one are fairly similar, but you might have a slightly better one here, blue than green. So you can look at your forecast in this way. So those are 4 different types of evaluations you can do on a straight-up probability forecast. And now I'm going to skip over to evaluating more your whole ensemble, not necessarily turning your ensemble into a probability forecast, but using the full distribution of your ensemble. So I think rank histogram is probably the most common type of evaluation I've seen done on ensemble forecasting. Has anybody used rank histograms on the ensemble? So they can be valuable. The idea is to look at, is your ensemble dispersive enough? And if it is, that means that your observations come from the same distribution as your ensemble does. And you can judge that by looking at a rank histogram. Ideal is flat, but this ideal diagram here is not exactly flat, because whenever you're taking a sample, what we're really looking at is not perfectly flat, but not statistically distinguishable from flat. And so you will see a little bit of variation here. What we generally see with ensembles, at least the ones that we evaluate, is that they are under-dispersive, and so what you get is this U-shape where your observation falls outside of the range of your ensemble more often than you would like it to. It's also possible to see some bias with these, where you just have one of these sides is very tall and not the other, and then that means it falls more to one side or the other. And then if your ensemble is too wide, you'll see more of a peaked distribution. Something looks a little more like a Gaussian. Rank histograms are certainly imperfect, and they can be fooled. So if you have, say, biases that cancel out in a big group, but that were conditional and you could separate them out, you might get a flat rank histogram without really having the right distribution. So they can fool you, but they still are a useful tool so long as you understand what you're evaluating. A spread skill diagram is another way of looking at your ensemble forecast. So when your ensemble is perfect, the spread of the ensemble is supposed to represent the error in your forecast. So you can look at the spread, look at the error, and see, are they the same? We would like to see them be the same. So here are 2 spread skill diagrams. In the top, they are not the same. We have considerably more error than we have spread in this one, where we've plotted the root mean squared error here in the blue and the ensemble spread down here in the black. And these are with confidence bounds on them so that you can look at the statistical significance of those. And then down here at the bottom, they're much closer and they overlap. So in this case, our ensemble spread does seem to represent the error in our observation that we see with the observation. So then our ensemble spread is about right. And again, these can be produced in MET and MET Viewer. There are a couple of statistics in MET that are not very highly used: the rank probability score and the continuous ranked probability score. And they are not used very much because they are specific for certain data formats. So the ranked probability score is when you have a multi-category forecast, so not an event or non-event, but you might have a precipitation type where you have 3 or 4 different categories. And then the continuous ranked probability score, where you have both a continuous ensemble forecast and a continuous observation. These are analogs of the Breyer score. So the Breyer score is really the same, but it's when you have a binary observation of an event and non-event, along with a probabilistic forecast. So these are analogs in case you have a different style of data. The CRPS has a nice geometric interpretation. So if your observation is here, this boundary line, and your distribution of forecasts has a CDF along this curve here, then the CRPS is the area of the difference between these, which is this little triangle here plus this triangle here. And so that's what the value of it is, and there's a formula for the integral of it, you know, over the cases. Sometimes you have to fit a distribution to your ensemble because your ensemble doesn't usually have a known distribution. It has a lot of value, so you maybe fit a normal to it and then do this integral. So these are basically mean squared error types of scores, but for different types of data. There is a score called the ignorance or the log probability score that was borrowed from information theory, where the idea is to count the number of bits that you would need to represent something. And so this score is also in MET, and I don't see it used very much, I think because the format of the forecasts has to be that you have a probability of a bunch of different events. And if you have that, the ignorance score is the negative log of that probability. In weather forecasting, you'll add those up over a domain and a large set of cases and average them out. And so in MET, you'll see a more complicated formula involving the averages of these. So that is the log probability score. Basically, in summary, I've just gone over 3 or 4 different types of plots and scores for probability or full ensemble forecasts. There's a table of them here, talks about what they measure, when to use them. This is just a quick reference for you in the future. And I'm assuming you guys will distribute the slides. And then there's a very long list of references because, of course, in this 10 or 15 minutes, I only barely told you anything about ensemble verification, which is in fact a very complex subject that you could spend years studying. And so with that, I will hand it back to John to talk more about the software. But if you have questions about verification, methods or interpretations, you can email me through MetHelp and I will answer statistical types of questions. And also it's a good idea to look at your references and papers. So thank you very much for your attention.
Thanks, Tressa. Okay, let's see. I have 3 minutes left, so I'll see what I can cover here. I want to bring us back to the ensemble stat tool here. In MET, it's both green and blue. Why is that? It does, what does the ensemble stat tool do? It reads gridded ensemble member files. So if you have a 10-member file or 10-member ensemble, you pass in, for a particular point in time, the files that contain the data for each of the 10 members. You pass in gridded and point observation files. So in PointStat and GridStat, in PointStat it handles point observations, GridStat handles grid observations, Ensemble Stat handles both of them. It calculates some things like the ensemble mean Tressa mentioned, or deriving probabilities from an ensemble. We call those relative frequencies. There's a lot of ways you can intelligently post-process your ensemble to generate ensemble products. The most simplistic way of all is just count up the number of ensemble members that meet some exceedance, some threshold criteria. So, for example, what is the ratio of your ensemble members at which precip is occurring? Say 5 out of the 10, so your probability forecast is 50%. That's probably a lousy probability forecast because it's probably not calibrated. There's all sorts of ensemble post-processing you could and should be doing. Ensemble Stat doesn't do that for you. I think there's a need in the community to have a package to make that easy to do. but it does the most simplistic relative frequency. The things listed here in blue are the statistics that Tressa already mentioned. So the ensemble continuous statistics line type, which is new in MET version 7.1, which isn't released yet, contains all the spread skill relationships, CRPS, that sort of thing. The rank histogram, relative position count, which is very similar to a rank histogram, but instead tells you how frequently the nth ensemble member is the best. So it keeps track of, if you have distinct ensemble members, it keeps track of which one is doing better than the others. Spread skill, output line types, and application of observation error is new in MET 7.1. So ensemble stat writes an ASCII file with things like the ranks and RELPs and a pit histogram, probability integral transform histogram, that sort of thing. But it also writes a netcdf file which contains these ensemble products, like ensemble mean and the probabilities that it generated. That's what makes it a pre-processing tool. So we take those probabilities and we're going to evaluate them in point stat and or grid stat. I'll skip over the usage here. This is just in our online or in the in-person tutorial. We go through the usage for each of the tool, the command line usage for each of the tools in a lot more detail. In the configuration file for ensemble stat, like all the other tools in MET, you can control what fields you want to verify. So here in the ensemble section, we say that we want to compute probabilities for 24-hour precip exceeding 0 and greater than or equal to 10 millimeters, reflectivity exceeding 35 dBz, and the U component of 10-meter wind exceeding 5 meters per second. So this is kind of what the ensemble section in the config file looks like for requesting those things. In the forecast section, really you can only compute rank histograms and those sorts of things for variables for which you have observations. So in general, you may want to compute probability forecast for many fields, but you only want to actually verify in ensemble stat a subset of them. So that's why they're listed separately. In the forecast dictionary, here we're listing that we want to just look, we want to evaluate 24-hour accumulated precip. I mentioned I had a previous slide about the output flag for grid stat and point stat. Here's the output flag for ensemble stat, where you select you turn on or off the line types that you want to show up in the output. The ensemble flag, you can control what variables are written to the output netcdf file. So here the ensemble mean, standard deviation, min, max, range, that sort of thing. In MET, we support, again, working with folks at NCEP, they do grid weighting based on the cosine of the latitude for global grids. So basically, if you've applied grid weighting, then you can write that out to the output here. When you run ensemble stat, this is what the command line might look like. Here you can either pass in all, in this example, we're running ensemble stat on 6 ensemble members and just passing them in literally on the command line. Alternatively, you can just have an ASCII file that lists the files that you want to process. You tell it what grid, point observations, that sort of thing to use. You run ensemble stat and it produces output. So here's a sample output rank histogram line type where if we have a 6-member ensemble, that means there are 7 possible ranks, and the counts for those ranks are listed here. These little thumbnails just show output like the ensemble mean, standard deviation, and these relative frequencies or probabilities that it derived. Here is an under-dispersive rank histogram. Is that right, Tressa? Okay. So it has the U shape, which we often see. This was made by MetViewer, I believe. The RELP line type, I already mentioned, keeps track of how often each individual ensemble member is outperforming the other members. So what are some recent updates? In MET version 7.0, which is the currently available release, we added some config file options in ensemble stat to one called skip constant equals true. So basically, if you're evaluating precip, you may want to look at all the points where everything's 0, which happens a lot, and just discard them from your analysis. So if you say skip constant is true, you can throw out all those points from your analysis. You can also do something called conditional verification, where we have the observation value for each point we have the observation value and n ensemble members, and you could say, well, I only want to evaluate where my observation is greater than 0, or maybe if I'm evaluating temperature, I want to condition my data and only look at the cases where the observation is greater than freezing, something like that. Upcoming in the MET 7.1 release, we've enhanced, in the config file examples, I showed you pulling data from the syntax for pulling data from grib1, grib2 files, that sort of thing. We're enhancing the config files to enable you to specify a Python script that will go, the user writes a Python script which goes and pre-processes their data in whatever way they like and loads it up into an X array with the right metadata, and we read that in memory. So that, I think, will open up Met to a lot wider range of applications. We're working on reading Go16 AOD data sets for a group at NOAA. We've added this new ensemble continuous statistics line type, and one big impact for ensemble stat is the use of observation error when doing ensemble verification. So this was hot off the press. Yesterday I've been collaborating with Jeff Beck, who works over at NOAA GSD here in town, and he's testing the software, a beta release of version 7.1 to make sure it's doing what we expect. Here's an example of a rank histogram that he generated without turning observation error on. And with observation error turned on, basically what we're doing is we're assuming that each observation has some amount of error with it. And we assume that error follows some distribution. So for example, we might say our observations of temperature, maybe if the temperature says 293, maybe it really is plus or minus 1 degree, something like that, following a normal distribution. So we use that error to perturb the ensemble member values, not the observation itself, which seems counterintuitive, but they've shown me the literature and convinced me that it's the appropriate thing to do. So you see this relatively U-shaped histogram and biased histogram now looks less U-shaped after applying observation error. Here is a line plot showing the spread in blue and the RMSE in red. In orange here, it's the RMSE with the perturbed ensemble member value, so the RMSE of the perturbed ensemble mean. The black is the spread, the spread of the perturbed members, and then the gray is a different type of formulation spread plus the square root of the variance. Don't worry about it. Okay, so you've run ensemble stat, you've generated this ensemble products file. You can feed it back into GridStat to verify the probabilities. We do the verification of probabilities using an n/2 contingency table. Tressa mentioned how you define your probability bins. So in the configuration file, you say, well, I want to evaluate my probability in, let's say, 25% bins. So that basically determines the number of rows of this column. And then you define a threshold for the observation value to decide whether the event occurred or did not occur. So that defines our 2 columns here. So as an example here, we have a probability of precip forecast from on the left, and our verifying analyses on the right. We say we want to evaluate probability of precip, define our probability thresholds in 25% bins, and then we're verifying against 12 hours accumulated precip. And the event for which the probability was defined is precip being greater than 0, so that's how we define our threshold in the observations. This is the config file entries that correspond to that. You'll notice here in the output flag, I've turned all of the line types off except for the ones being with P, which is the probabilistic output. These are the line types that contain the statistics that Tressa went over. So PCT for the probabilistic contingency table counts. PSTD contains the Breyer score, reliability, resolution, and so on. PJC contains the calibration, refinement, and likelihood, and PRC is the points that correspond to this rock curve. In MetViewer, we load the PCT line type and generate all the probabilistic plots by aggregating those tables and deriving statistics from them. I won't talk about the ECLV line type is the economic cost loss value line type, which we didn't have in Met until we were working with folks at NCEP that used this econ line type. So we collaborated with them to implement the same logic in Met. And I'm well over my time. Here is a URL for a tutorial that was put out there by the Developmental Testbed Center doing end-to-end numerical weather prediction modeling using software containers. This includes containers from Met and MetViewer. If you're looking for a place to get started and you want to get some sample data up and running quickly, I'd suggest looking here, and that'll give you that'll give you an instance of MetViewer running directly on your laptop where you can play around with making different types of plots. I'll say thanks there and ask for any questions.
Question or two. I'll be around the rest of the day as well
Yep.
during the break and lunch as well if you want.